Good morning students, welcome to our online video class of chemistry. In this video, we will discuss about what is order, molecularity and about factors influence the rate of reaction. The next topic is factors affecting rate of reaction. The rate of chemical reactions influenced by number of factors such as concentration of the reactant, temperature of the reactants, catalyst, pressure, surface area, exposure to radiations, nature of reactants, etc. Let us discuss these factors. Effect of concentration. When concentration of reactant increases, rate of reaction also increases. In all chemical reaction, irrespective of their nature, as reaction progresses, the reactants are consumed and the products are formed. This means that as the chemical reaction proceeds, the concentration of the reactants keeps on decreasing and rate of reaction is also found to decrease, while those of product increases. Concentration of product increases. The exact dependence of reaction rate on concentration of reactants in particular reaction is determined experimentally. Let us consider a chemical reaction. A gives the product. In this reaction, the rate of reaction is only depends upon the concentration of reactants. That is, rate of reaction is proportional to molar concentration of A. That is concentration of reactant. Or we can write it as rate equals K into molar concentration of A. When A represents the molar concentration of A and K is the constant or proportionality and is called the rate constant. It is also called velocity constant or specific reaction constant. And an expression which relates the rate of reaction to the concentration of reactants is called the rate law. What is rate law? Rate of reaction is directly proportional to concentration of the reactants raised to some power which may or may not be same as stoichiometric coefficient of the reactants in a balanced chemical equation. Consider a general reaction. A plus B gives the product. Suppose by experiment it is found that rate of reaction depends upon X concentration terms of A and Y concentration terms of B. Then the rate law of reaction will be rate equals K molar concentration of A raised to X and molar concentration of B raised to Y. K is called a rate constant. X and Y are exponent of concentration term A and B. X and Y may or may not be equal to stoichiometric coefficient A and B. Concentration of each of the reactants involved in the reaction is unity. That is A, molar concentration of A, molar concentration of B equals 1 moles per liter, then rate equal to K. So rate constant may be defined as the rate of reaction when concentration of each reactant is unity. Now what is rate law? Rate law is directly proportional to concentration of the reactants raised to some power which may or may not be same as stoichiometric coefficient of the reactants in balanced chemical equation. Rate equals K molar concentration of A raised to X into B raised to Y. Next topic is order of the reaction. Order of reaction is the sum of the power of concentration term in rate equation. For example, if the rate of general reaction of type AA plus BB gives product, and it is given by rate law, rate equals K into molar concentration of A raised to X into molar concentration of B raised to Y. Then order of the reaction with respect to A is X, and order of the reaction with respect to B is Y, and overall order of the reaction equals X plus Y. This is the overall reaction, overall order of the reaction. The order of the reaction is an experimentally determined quantity. The reaction, in other words, order of the reaction is the sum of the power of the concentration of the reactant terms in experimentally determined rate equation, and it can have value of 0, integral values as well as fractional values. Rate equals K into molar concentration of A raised to X into molar concentration of B raised to Y. Here X and Y represents the order with respect to reactants A and B, and the overall order is X plus Y. Let us look some examples for reactions of different orders. First order. In a first order reaction, the reaction rate depends upon the concentration of one reacting species. That is, rate equals K into molar concentration of A. The rate depends upon one concentration. Example, N2O5 gives 2NO2 plus half O2. The rate of this reaction is R equals K into N2O5. Then what is the order of the reaction? Order equal 1. The order with respect to N2O5 is 1. So order of the reaction is 1. And another example. H2O2 hydrogen peroxide. H2O plus half O2. Rate equals R equals K into molar concentration of H2O2, and order of the reaction with respect to H2O2 equals 1. This is the example for first order reaction. And second order. In a second order reaction, the reaction rate depends upon the concentration of two reacting species, same or different. That is, rate equals K into concentration of A square. Example, 2HI gives H2 plus I2. K equals Hi square. Order with respect to Hi equals 2. Then CH3 CO C2 H5. Ethyl acetate plus NaOH. This is alkaline hydrolysis, saponification of ethyl acetate. Gives sodium acetate, that is CH3 COO Na plus C2H5OH. Rate equals, this reaction rate equals molar concentration of, rate equals K into molar concentration of CH3 COO C2H5 into molar concentration of NaOH. And overall order of the reaction equals X plus Y, that is 1 plus 1 equals 2. An example for third order reaction is 2NO plus O2 gives 2NO2. For third order reaction, in third order reaction, the reaction rate depends upon the concentration of 3 reacting species. It may be same or different. That is, rate equals K into molar concentration of A raised to 3. Then in this example, rate equals molar concentration of NO raised to 2 into O2. Here the order with respect to NO is 2 and order with respect to O2 is 1, and total overall order of the reaction equals 2 plus 1, that is 3. Zero order reactions. The reactions implies that reaction rate is independent of concentration of the reactant species. And these reactions are mostly of heterogeneous nature carried on the catalytic surface. For example, thermal decomposition of ammonia on the surface of platinum catalyst under high pressure. This is the reaction. 2NH3 gives N2 plus 3NH2. Thermal decomposition of ammonia in the surface of platinum catalyst under high pressure. And in this reaction, platinum acts as catalyst. Under high pressure, the surface of metal gets saturated with the ammonia molecules. This means that any further change in reaction condition will not change or alter the amount of ammonia or the surface of the catalyst. That means the reaction rate is independent of molar concentration of the reactant. It is zero order reaction. And rate equals K into molar concentration of ammonia. And fraction order reaction, example is reaction between hydrogen and bromine to form hydrogen bromide. H2 plus Br2 gives 2HBr. Here rate equals K into H2 into Br2 raised to 1 by 2. Then order of the reaction equal 1 plus half, that is equals 1 1 by 2. And molecularity. Molecularity of a reaction. What is molecularity of a reaction? The molecularity of a reaction is defined as the number of molecules or atoms or ions which collide simultaneously to bring about the reaction. Or other words, molecularity of a reaction is simply the number of reacting species, such as atoms, ions or molecules, involved in an elementary reaction which must be collide simultaneously. If a reaction involves decomposition of only a single species, the molecularity is 1, or it is called unimolecular reaction. For example, NH4NO2 gives N2 plus 2H2O. Why it is called unimolecular reaction? The reaction involves the decomposition of only a single species, that is ammonium nitrate. Then, if the reaction involves the collision of two species, the molecularity is 2, and it is called bimolecular reaction. For example, dissociation of hydrogen iodide is a bimolecular reaction. 2Hi gives H2 plus I2. This is a bimolecular reaction. The reaction involves the collision of two species. Here, two molecules of Hi are collided to form H2 and I2. And if three molecules are involved in the collision leading to the formation of the products, then the molecularity is 3. It is called trimolecular or termolecular reactions. Example, oxidation of nitric acid. 2NO plus O2 gives 2NO2. Here, 3 molecules are collided to form the product. 2 molecules of NO and 1 molecule of oxygen. Bimolecular reaction involves simultaneous collision between two species. Example, dissociation of hydrogen iodide. 2Hi gives H2 plus I2. And trimolecular or termolecular reaction involves simultaneous collision between 3 reacting species. Example, 2NO plus O2 gives 2NO2. But we know that there are number of reactions involving a number of molecules of reactants in balanced equation. Such reactions are supposed to take place in 2 or more steps and are called complex reactions. I hope all of you understand what we learned today. In next class, we will discuss about complex reactions, first order reaction, second order reaction, and the factors which influence rate of reaction such as temperature and catalyst.